Testing, testing, take two. There we go. All right. Hello, everyone. Happy Friday. How many of y'all are going to the game tonight? Fair number. Awesome. Very cool. Well, I appreciate you coming today. But yeah, so it's 1:50. Why don't we go ahead and get started here? So administratively, kind of same old, same old. You have some homework due tonight, so make sure you get that done earlier rather than later. I've seen a lot of activity on Piazza, so it looks like folks have been aiming to get that done yesterday and the day before. So try to get as much of it done as you can. Let's see, another administrative thing, right? There's this pre-course survey. I think the majority of students have taken this already. There's a link to that on the homepage of D2L. Now under the announcement section, but that's due next Wednesday. I'll try to give some more announcements about that. But it's one of the few extra credit opportunities that we have in this class. So I don't want you guys to miss out on any extra credit. So please put that in your calendar or make sure that you do that. The initial course survey is a pretty fast one. So it shouldn't take you more than 2 minutes and change or so. So I would just get that done sooner rather than later. I think that's all of my administrative stuff. Any questions about the class in general? Anything before we get into the math for today? Okay. Paranoid that there's a hand that I'm not seeing, but all right. All right, let's talk about the math then for today. So today we're going to talk about the other product that you can reasonably do with vectors. And again, kind of it's designed to solve a kind of natural question. And so for the dot product, this thing was designed to answer the question, what is the angle between a couple of vectors? And it turns out this quantity keeps on coming up. And so we might as well call it something. And it turns out it also satisfies a lot of the conditions that we know and love about multiplication. So we'll call it a product of types. And hence we get the dot product. Similarly with the cross product, as we talked about in the pre-class videos, when you have two vectors that are hovering in space, this can make like a two-dimensional plane. So you're using 2 out of the 3 dimensions quite often when you have two vectors. So the question is, well, what is that third dimension? And maybe a good and reasonable way to answer that is, what's another vector that is perpendicular to that plane? That would give you that kind of third dimension. It's kind of like, in 12.1, when you have the XY plane, we developed the z-axis or the k unit vector, right, as another vector that's perpendicular that gives us this third dimension. So that's essentially what the cross product is doing, is answering the question, where is that third dimension? How do we find that third dimension? And you do it with a cross product. So when you go and you calculate out a cross product, you do a determinant, 3x3 matrix determinant here. I do the plus minus plus method. I talked a little bit about in the video how there is another method that you could reasonably do, but the problem is this only works for 3x3 matrices. So if you ever wanted to take a determinant of a 4x4 or a 5x5, this diagonal method doesn't work. And so that's why I prefer this other method, because then if you have to take higher level math classes or engineering classes or what have you, where you may need to take a 4x4 determinant of a matrix, the method that we're teaching here works. So I'm going to stick with that method, but if you see this other method, it is viable for 3x3 matrices, just not anything bigger than that. All right, so we calculate out the cross product using determinants. We go over a few properties. Again, we have that just like the dot product, the cross product has some nice formula to it. So in this case, when you take the magnitude of it, instead of a cosine there, right, you have a sine. And if the cross product yields 0, right, that means that your two vectors are going to be parallel rather than perpendicular. So again, if the dot product is 0, you get perpendicular. If the cross product gives out 0, and again, the easy way to do that is with the magnitude, then that means that they're parallel. A few more quick examples. Talked again about the right-hand rule, but that's the pre-class videos in a nutshell. Any questions or anything that wasn't quite clear about the pre-class videos when I went over it, well, before class? All right. Well then, why don't we go ahead and we can jump into the new stuff. So starting off, again, why don't we calculate out a cross product? And better yet, we're going to verify that this thing really is perpendicular to our two given vectors that we have. So again, anytime I want to calculate out a cross product, I'm going to be doing a determinant of a 3x3 matrix. In my first row is always these standard unit vectors, the I, J, K unit vectors. In the second row, you get whatever vector comes first here. So in this case, it's A, 1, 1, -1. And then in my final row, I get the whatever vector comes second here, in this case, 2, 4, 6. Whenever I write out my cross product, and we're going to be doing cross products all throughout the semester now, all the way through chapter 16. And so I get worried about messing these up, in particular because it goes, you have positive stuff along with the I, and then you have negative stuff along with the J, and then you have positive stuff along with the K. So it goes plus, minus, plus. And so I usually write this out, first, so that way I'm not forgetting that negative sign. It's a common mistake that I see quizzes, exams, homeworks, things like this, is that students, and especially, I mean, when you're in a section that's all dedicated to the cross product, most people get it right. But it's later on, when you're trying to use this to do 20 extra steps or whatnot, that's when it seems to, you forget the negative sign there. All right, so in order to get these values, we're going to cross off the things in the first row and first column. And then we're going to do this 2x2 matrix determinant. So we're going to do these diagonals multiplied together, and then we subtract. So my first diagonal is top left to bottom right. So that's 1 times 6. That's going to be 6. And then we subtract away the top right to bottom left. So we have -1 times 4. So that's going to be -4. So minus a -4 is going to be +4. So that's all the stuff with I. Again, this was crossing off the first row and the first column. And now we're going to move our way across. So let me go ahead and erase this here. We're going to cross off, again, the first row and now the second column. And those numbers that are left over, we have a 1, a -1, a 2, and a 6. And again, we're going to look at the diagonals there. So 1 times 6 is going to be 6, minus 2 times -1 is going to be -2. So when I subtract away a -2, that's going to be the same thing as adding 2. And then finally, we're going to cross off the first row, third column. So we work our way across this first row, getting our I, our J, our K. And here we're going to have 1 times 4 is going to be 4, minus 1 times 2 is going to be 2. So my final answer here is going to be 10, -8, and 2. So again, the stuff next to the I's, that's your first component. The stuff next to the J's, that's your second component. The stuff next to the K's, that's your third component. And again, we have the -J. Question, yeah. Yeah, so there's, and as you go to higher level determinants, what there really is a -1 raised to the row number plus the column number. So when you're doing the first row, first column, this would be -1 raised to the 1 + 1 or second power. So that means it's going to be positive, right? And then when you move over to the second column, that's where you're going to have -1 raised to the third power altogether. And then finally, when you move over to the third column, you get 1 + 3 is going to be 4, so it's going to be positive again. And so this continues. If you have higher level determinants, like of a 4x4 or a 5x5 matrix, this continues. It's a little bit, that's probably as much detail as I want to go into as kind of why you have to have this plus, minus, plus. But the next step is you could say, well, why is that there, right? And you could kind of take up all 50 minutes kind of going down this rabbit hole sort of deal. But yeah, that's the trend. Okay, so my claim is this right here is my cross product. So this is my A cross B that we were tasked with finding. And then it asks us to verify that it actually does the thing we claim it to do. That is, it's this other dimension. So we want it to be perpendicular to both of our starting vectors. So again, kind of in our original picture that we did in the pre-class video, maybe we have vector A and vector B. You can imagine that these would make some plane. They exist together in some plane. And we want some vector that is perpendicular to these things. It's perpendicular, in fact, to the entire plane there. So we want it to be perpendicular to A and perpendicular to B. So how do I check if two vectors are perpendicular? Like, how do I check that this is actually perpendicular to A? What was the test for that? Yeah? Dot product, right? So we want the dot product to be 0. If the dot product is 0, that means they're orthogonal or perpendicular to one another. So I'm going to go ahead and take my result, 10, -8, 2, and I'd like it to be perpendicular to A, 1, 1, -1. But better yet, I also want it to be perpendicular to B. So I'm going to check both of these things and verify that the vector that I found is actually perpendicular to both of these other vectors. So if I was to go ahead and calculate this out, what we get, 10 -8 -2, that indeed is equal to 0. So yes, it's perpendicular to A. How about for B here? Well, I would get 20 -32 plus 12. So yes, this indeed is equal to 0 as well. So this right here is the check to verify that what we have is indeed orthogonal or perpendicular to our two starting vectors. So that's this bit here. Verify that it's orthogonal to our two starting vectors. All right. Any questions on this problem here? Okay. Well, again, this thing is labeled as a product because it satisfies a lot of the conditions for multiplication that we know and love. All except one, really. The cross product doesn't quite work when you have the commutative property. So if you switch the order, and instead of A cross B, you do B cross A, it turns out you're going to be off by a negative sign. And again, this comes from the right-hand rule here. So maybe I could spend a little bit of time looking at the right-hand rule one more time. And actually, let me relabel this, like this to be vector A and this to be vector B. So I'm going to do my best to hold my hand up to the screen here and maybe also sketch on the iPad as well. But the right-hand rule says, using your right hand, you want to go through first whatever your first vector is, and then through whatever your second vector is. So in this case, it's A cross B. So I want to go through A first and then through B using my fingers of my right hand. So if I do that, going through vector A first and then through vector B, my thumb points in the direction of the cross product. So this is going to be our A cross B up here. So again, maybe a little sketch, thumb pointing upward, fingers curling. Really good at drawing, guys. There we go. Something like this. On the other hand, if I was tasked with finding B cross A, notice if I keep my thumb pointing upwards, there's no way that I can really have my fingers go through B first and then through A. They're going to hit A no matter how hard I try. So the only way to really get it to my fingers to hit B first and then A is that I need to flip my hand upside down. Then when I rotate my right hand fingers around here, if my thumb's pointing downwards here, then be like this, my fingers can go through B first and then through A. So therefore, again, this would be perpendicular to these two vectors, but pointing downward rather than pointing upward. So again, the only difference really between these, because the magnitude will be the same, is that one points up and one points down because it's based off of this right-hand rule. So that negative right there just takes your direction and flips it. So if it was pointing up, it's going to point down. If it was pointing down, it's going to point up, etc. Besides this, everything works out for the cross product in terms of our favorite multiplication rules. So for instance, we have associativity. You could go ahead and break out these scalars R and S, and then do your cross product. 0 times our vector is in fact 0. Remember, the output for a cross product is always a vector. So when I say 0, it's the 0 vector, or that's equivalent to, right, 0, 0, 0. There is a distributive law, but since it matters the order in which you multiply, you must maintain that order. So for instance, if I was to go ahead and distribute this here, A needs to stay on the left-hand side. So whenever this comes up, this is called a left-hand distributive rule or a left-hand distributive law. So A is on the left, but there's also a right-hand distributive law. So in this case, A is on the right. I know that guy. There we go. All right. Any questions here? Yes. Yeah.
It says, like on the previous page, says if the cross product, if the magnitude of the cross product is equal to 0.
Yeah.
So does that mean like what you were talking about there, like the 0 vector?
Yeah. Sorry. Once you apply a magnitude to it, right, then it's a number, right? Because you're going to take all of the pieces, you're going to square them, add them together, throw them under a square root. So that right there truly is a scalar 0. But you could have, oops, that was on our pre-class video. You could have equivalently said A cross B is equal to the 0 vector. That would have been fine too, because the 0 vector is going to give you the magnitude of 0. As soon as you get one component that's not 0, right? Because you're squaring everything. So it's turning positive. You're adding all those together. Then you're taking the positive square root, right? As soon as something's non-zero, the magnitude is going to be positive. So, yeah, good question. And I mean, when we actually go and we ask, if two vectors are parallel to one another, the easiest way is not to use the cross product, right? Because the cross product is somewhat time consuming. The easiest way to say if two vectors are parallel is that they should just be scalar multiples of one another. So it should just be a scaled up version of the other vector. So in practice, that's the fastest way to determine if two vectors are parallel. Yes. I mean, the book teaches this way, but yeah, if you know some other way to apply the right-hand rule, so long as you're not confusing yourself, then yes, that's fine. Yeah.
Vector that wasn't really along one of the planes. So like if it was like up in the Z.
Yeah, so I mean, then you're, I can hold up a couple of pencils or something like this. Let's, and you could do this at home if you're watching the video as well. So I mean, if we have, let's suppose that I have two different colored pencils. I have white and green here, and I would like to find the cross product between these things, right? And so I'd like to find the cross product between the white pencil first. We'll say this is vector A, and then the green pencil second, right? And you can see that this one's kind of going up into the Z-axis and all that sort of stuff. So again, it's going to be perpendicular to both of these things. So it's going to be at 90 degrees. So it's either going to shoot out to my left here, maybe your right, or my right, your left, right? So that's the only way you can get it perpendicular to both of these, at 90 degrees to both of these. So I'm going to go ahead and using my right hand, right, I'm going to go through maybe the white pencil first with my fingers, then through the green, right? And then we can see my thumbs pointing out to my left, right? And so therefore, the cross product would give this one. So no matter how the vectors are oriented, even if they're not laying flat, kind of from your perspective, you can still apply the right-hand rule. Yes?
If you're crossing the green pencil with the white one, then would it go the other way?
Yes. Yep. So if I was doing green first and then white, right, my fingers would have to go through the green first and then the white. And the only way I can get this to work out is my thumbs pointing to my right. Yeah. All right, well, let's go ahead and apply these properties here. So I've given you kind of quickly here a cross product so that you don't have to calculate it all out. And then my question is, well, given this piece of information, can we use that along with our properties in order to get something else? So in this case, right, we can see the only thing that has changed is that I flipped the order. So instead of 110 coming first, 110 comes second, right? Otherwise, they're the exact same. And so therefore, my result should be off by a negative. If I'd like to go ahead and do my scalar multiplication and multiply through, this would be 2, -2, -1. The second one here, it's quite similar, except for, let's see, it looks like my second vector is exactly the same, but my first vector, instead of 110, it's 440. So it's been scaled up by a multiple of 4. So in particular, I could write this as 4 times my 110 times, and I'll make it very suggestive here, 1 times my 3, 4, -2. And according to property B that we have here, right, with R times some vector, so in this case it's 4 times some vector, and then I do the cross product with some S, which happens to be 1 in this case, times my other vector, right, so in this case B, I suppose, that you can go ahead and take those scalars out in front, so this would be just 4 times 1, that would be 4, times the cross product. So my cross product, again, we already know is -2, +2, 1. And so if I'd like to simplify this, I could write this as -8, +8, 4. So this is a a little bit of a silly example, right? I mean, because you could just calculate this out by hand, and you don't need to know these theorems. However, if I wanted to make this, some more conceptualized, quiz or exam question or whatnot, I could give you all the same thing. I could write this as capital A here and, I don't know, capital B here or something like this. So that way you can't do the calculations. And then this would be capital A, and this would be what, -B here sort of deal. So then it would really force you to know these properties rather than just being able to calculate it out. Because again, now we don't know what A and B are in this case. So you'd have to use those properties. All right. Any questions on this one here? Well, then I'd like to talk about an example of this, a specific use case. And one thing, and especially when you have like parallelograms in space or whatnot, you may have noticed that the area of the parallelogram formula is actually quite similar to our cross product formula that we have. So maybe in your favorite geometry class or whatnot, you would have gotten that along the lines of the area of a parallelogram is x times y times the sine of the angle between those sides. So if you had a parallelogram with side lengths x and y and angle theta, right, this is the area formula for a parallelogram. Instead, if you wanted to do this with vectors, so now I have vector A, vector B, if I want to find the area generated by this parallelogram between these two, well, the side length of vector A would be the magnitude of A. The side length of vector B would be the magnitude of B. And then you have the sine of the angle between these things. This is the exact formula that we gave in the pre-class video for the magnitude of A cross B. So then, I'd like you to try to apply this formula, and maybe I'll give you a 60-second head start or so. But find the area of the parallelogram generated by these two vectors, u, which is given by I negative j, and v, which is given by j plus 3k. Another 30 seconds or so, get as far as you can. All right, let's talk about this one together. First thing here is that, again, if maybe you're perfectly happy with the IJK notation, in which case you can leave it as is. If, however, you prefer kind of the standard angle bracket notation, you can certainly convert these into those angle bracket notation for vectors. So again, the key thing here is that u is missing a k component and v is missing the I components. So there's some zeros that maybe you don't feel as much with the IJK notation. Then we need to set up, right? And we're asked, really, we need to do a couple of things. We need to take a cross product, and then we need to take the magnitude of that cross product. If I already knew what the angle was between these vectors, right, I could use this formula right here. But this kind of would require us to, well, calculate out those magnitudes and then also know what the angle is between these things. So it is viable. It just takes a couple extra steps. However, we can take the cross product and then take the magnitude kind of a little bit quicker here. And after all, today's class is a class about taking the cross product. So we'll stick with that method. So again, I started to take my cross product. I chose probably I hope I chose a unpopular choice for my first vector versus my second vector, right? I put v in my second line here, and I put u in my third line, right? I suspect that many of you probably didn't choose that ordering, right? You probably put u before that and then v in the last one. And so consequently, right, my answer right here is probably different than many of yours, right? If you had done it maybe the other way, I suspect that you would have gotten -3, +1, right? So our intermediate step here will be off, but luckily this is not the final answer, right? It doesn't make much sense to say that the area is this, right? Because the area has to be like a number, some positive number, right? It makes sense to say that the area of some shape is 5. It doesn't make sense to say that the area is a banana, right? You have to have probably a positive number. You can't have a vector or something else. So, okay, well, we need to turn this into, right, a number. And we have a vector here. So the way that we're going to do this is with the magnitude. I guess our vectors here were labeled u and v. And I guess in my particular case, I did v first and then u. And so my answer, once I square all these things and add them together, is going to be root 19. And that, I would hope, is the same answer, even if you did it in the opposite order, that everyone would get, right? So if you found u cross v, and I found v cross u, our intermediate steps may be different, but once we take the magnitude, right, we should all get the same answer. Any questions on this one? Yeah. Mhm.
I hat, J hat, why do you just do I J?
You can use I hat, J hat. Typically, the hat indicates that it's a unit vector. And they are unit vectors, by all means. It's just, so that's kind of just a reminder. At least, and different textbooks treat these things differently, right? And so it's kind of, if you write a popular math or physics textbook, right, and you have your own notation, then it kind of sticks a little bit more. But I mean, different authors may choose different notations depending on who's authoring the book. So if you get popular enough, though, then it sticks. All right. Any other questions? Okay, well, I have another problem here then for us. Find the area of this triangle. I'm going to go ahead and draw out a bit of a crude picture here. Let's suppose that this is P, Q, and R. We know how to find the area of a parallelogram generated by two vectors. So I'd like to imagine, right, if I had maybe vector PQ, which I could figure out what that vector is, and PR, then the parallelogram generated by these two is going to look like this. Right, it's just a couple extra copies of those vectors, the same sort of parallelogram that we drew out when we were doing vector addition in 12.2, for instance. So this would be the parallelogram generated by PQ and PR, those two vectors. So I hope now with this picture, right, we are interested in finding the area of a triangle, PQR, and we know how to find the area of the parallelogram. The answer is going to be, once we find the area of the parallelogram, we just multiply by what? 1/2, right? So yeah, that's going to be the game here. So we can find the area of a triangle now just by doing the same technique, but then multiplying by 1/2 at the end. So maybe let's do this one together. I'm going to start off by finding my vectors PQ and PR. So again, these are displacement vectors. Whenever I go out and I try to find displacement vectors, right, I usually do the ad hoc method, which is just I think about it logically, component by component. So if I start off at P and I end at Q, right, I start off at 1 and I end at -2, that means I must have taken 3 steps backwards. If I start at 0 and I end at 1, that means I must have taken 1 step forward. If I start at 1 and I end at 3, that means I must have taken 2 steps forward. But again, if you're someone who likes memorizing formulas, right, this is just the ending point subtracted the starting point, or the initial point. We can play the same sort of game here with PR. So if I start at 1 and I end at 4, that means I must have taken 3 steps. If I start at 0 and end at 2, I must have taken 2 steps. If I start at 1 and end at 5, that means I must have taken 4 steps to go from P to R in each component. All right, so now that I have my vectors, I can go ahead and find the cross product. So PQ cross PR. But again, no one tells you that you have to find it in this particular order. Some of you may decide, well, I want to do PR cross PQ, right? And then your answer, your intermediate answer may be slightly different than ours, right? And that's perfectly fine, because when we go and we calculate out the magnitude, we'll all have the same answer. So again, I's, J's, K's. PQ, PR. Stuff with I's minus stuff with J's plus stuff with K's. Crossing off that first row and first column, we're going to have 4 minus 4. Again, I'm looking at the diagonals, top left to bottom right, subtract away, top right to bottom left. Next up, crossing off that first row and second column to get all of our J information, that's going to be negative 12 minus 6. And then finally, crossing off the first row, third column, we're going to have negative 6 minus 3. So we're going to have 0, negative 18, but there's that extra negative sign. So positive 18, and then negative 9. So if I want the area of the triangle here, this is going to be, again, we need 1/2, and then we need the magnitude of this vector. So 0 squared will be 0, 18 squared will be some big number, negative 9 squared will be 81. So without a calculator in hand, by the way, if you type this into WebWork, it would tell you that it's correct. So if you don't have a calculator by hand, in hand, that you could also type this in. But if this was like a D2L quiz or an exam or whatnot, again, a calculator is required for this class. You should have a TI-30 calculator or something equivalent. TI-83 or TI-84 is fine, right? Plug that in and round to 3 decimal places. But again, even if you didn't have a calculator, right? Let's say your batteries died or whatnot, you're still submitting partial credit work, right? For these sorts of questions in D2L and whatnot. So for quizzes and exams, you would still submit your partial credit work. And so if you got this far, right, you're getting 90% plus of the points. So I mean, if this is a 10 point question, you're getting at least 9 points, maybe even 10. It depends on how the grading rubric is written. All right, any questions on this one? Yes.
QR, would that affect our answer at all?
If you did QR, yeah, it may affect your answer, right? Because then if you did, I'm assuming you did PQ and then QR, right? So if you did PQ, and I'm going to go ahead and shift this up PQ so that way it's kind of starting at Q now, and then QR, what you're doing is you're finding the area then of this triangle right here. And it's not obvious to me that this triangle would have the same area as the other triangle. Maybe it does, but we'd have to think about bases and heights and all that sort of stuff and maybe be quite clever, but it's definitely a different triangle. So you could get a slightly different answer. Again, unless if there's some, maybe from our geometry days, this is good old like SAS theorems and ASA, and right, we'd have to go back to our good old geometry proofs to verify. Yeah. QRQP would, yeah, certainly work. So if you did oops, that's my highlighter here. So if you did vectors QP and QR, then yes, then we're dealing with the same triangle. Yeah. Yeah.
Matter what choose or vertex you choose. It just matters that you choose the 2 vectors that come out of the same vertex.
Exactly. Yes. So no matter what, you have to choose vectors that come out of the same vertex. I chose P just because, I don't know, it's first sort of deal. But if you like both of your vectors originating out of Q, that's fine. If you like both of your vectors originating out of R, that's also perfectly fine. And this is the same sort of deal. I've seen this question show up on Piazza a couple times as well about right now, right? One of the homework problems has you doing something similar. You have a triangle with P, Q, and R, and you want to find those angles, right? What is angle P? What is angle Q? What is angle R? And the same rules apply, right? If I want to find angle P, I should have both my vectors that are originating out of P. If I want to find angle Q, I should have both my vectors originating out of Q. If I want to find angle R, I should have both my vectors originating out of R. All right, good. Any other questions? Yes.
4 points then. Would we like still use, through those points, the shape or not?
What kind of shape are you giving me with 4 points?
Square, for example, like a trapezoid or something like that. So I know that's one of the bugger questions, that's why I'm asking.
I guess it would really matter what the shape is. So I would hope that if they do give you 4 points for a Weber question, that they would tell you, is this thing a parallelogram? Because in which case, if it's a parallelogram, we can solve this quite quickly, right? If it's a square, squares are a generalized form of parallelograms, but they have a much easier formula, right? So if it's just a square, you could find the length of one of these vectors, right, by just taking the magnitude, and then you could just quantity square that, because for a square, the area formula is a lot easier because that theta here is 90 degrees. So again, sine of theta, sine of 90 degrees is 1. So that would make that very easy. If it's a shape like a trapezoid or whatnot, this gets more complicated. But I don't remember a question where they gave you like a trapezoid or something. But hopefully it's just like a parallelogram or something. Yeah, but it would really matter on the shape. All right, good. Well then, I have another question here, and then another kind of more real-world example of how cross products can be used. So I'd like to find 2 unit vectors orthogonal to both of these given vectors. So I'd like to start off by just trying to find maybe one vector that's orthogonal to both of these vectors. So I guess I'm going to go ahead and write these things. Maybe I'm going to name them. Vector A is going to be 0, 1, -1. And maybe vector B here is going to be 1, 1, 0. And I'd like to find a vector that is perpendicular to both of these, or orthogonal to both of these. Luckily, that's exactly what the cross product is designed to do. So I'm going to go ahead and calculate out A cross B. I'm going to get stuff with i's minus stuff with j's plus stuff with k's. Crossing off the first row, first column, it looks like I have 0 minus -1. Crossing off that first row, second column, it looks like I have 0 minus -1. And then finally, crossing off the first row, third column, it looks like I have 0 minus +1. So again, just calculating out those diagonals and subtracting. So my vector here is 1, -1, -1. So this is certainly a vector, and we could even verify that it's perpendicular to both of these using the dot product, right? If we take the dot product with these original ones, we should get 0, and that would be a nice way to verify that. But notice that we don't want just one vector. We actually want 2 vectors, and better yet, we want them to be of length 1. So I'd like them to be unit vectors. So I guess maybe the first thing is, how could I turn this into a unit vector? Well, you're supposed to divide by something, right? Just divide by its magnitude, right? So yeah, so we need to divide by its magnitude. So if I go ahead and I calculate out the magnitude of this thing, we would have the square root of 1 + 1 + 1. So that's √3. So that means maybe one unit vector would be 1 divided by √3 and times this. Which, by the way, if this was a web work question, it would perfectly, accept this. You could simplify if you'd like, right, by just distributing the scalar to each piece. 1 divided by √3, -1 divided by √3, -1 divided by √3. So either one of these, by the way, web work would accept. All right, so now I found one unit vector. Someone give me, how can I find my second one? Yeah, do you know? Multiply by -1, right? Because now it's just flipped. And so essentially this is, instead of finding A cross B, we're finding B cross A, but we're doing the fast way, right? We're just multiplying by -1. So yeah, maybe a second unit vector would be just multiplying by -1. And it's going to have, like, the vector would be -1, +1, +1. When you find the magnitude of that, it's going to be the exact same magnitude, √3. So in fact, when you try to make it a unit vector, you're going to go through the same sort of steps. 1 divided by its magnitude times this vector. And if you'd like to, just as before, you can distribute. So these right here are two different unit vectors, and they are both perpendicular or orthogonal to our starting vectors. And again, you can take the dot product to verify that if you'd like. All right, any questions on this? All right, well, the last application here will be for torque. So in this case, we have some maybe torque going in through this bolt, I suppose. And we have some crescent wrench and whatnot. This has a radius and we're applying a force. If you did this in your favorite physics class, you may do that this is maybe R times F times the sine of the angle between these things. And the direction's going kind of into the page here. Now that we're doing this with vectors, right? If we have vectors, bold R and bold F and whatnot, then this is going to be given by, these would be magnitudes. And the actual torque here, which I'm going to use maybe tau, is going to be given by R cross F. So you can see that the magnitude here is exactly what it would be for our cross product. And we're going into the page here. So quick example related to this. Find the magnitude of the torque generated by the force F at pivot point A in the figure below. So we're pivoting about A here. Looks like it's 5 feet off that. We're applying this force at point B. And we're just interested in the magnitude of the torque here. So the magnitude of R cross F, that's going to be the magnitude of R, the magnitude of F times the sine of the angle between them. Notice that I didn't get particular vectors, right? If they gave me vectors for these things, then I guess I could figure out AB. That'd be not too bad. But then I could calculate out the cross product and then its magnitude. But in this case, I do have lengths, right? The distance between A to B is 5 feet. So again, the radius here is going to be 5 feet. That's how long that is. That's the length of that vector there. We have a force of 10 pounds. Again, I don't know exactly what that direction is here, but I know the length of it is 10 pounds. And I have the sine of, it looks like the angle between these things is 110 degrees. So I guess we would have to change our calculator to degrees really quick and calculate this out and then switch it back to radians soon thereafter, because again, the majority of things in this class are going to be in radians. But this is going to be 50 sine of 110 degrees. And the units here are foot-pounds. I think this is around maybe 47. If you have a calculator, you can verify for me. Around 47, right? A quick side note. If I was to truly calculate or to draw R here, R is this radius vector coming from our pivot point to our end point here. And if I was to align these so that now both of our vectors have the same starting point. So if I was to pick up this R and move it over so that they both have the same starting point here. Notice that in my picture here, my theta is actually this theta right here. And yet we got this theta over here of 110 degrees, right? I guess knowing that these two angles for a straight line should sum up to 180 degrees, that this should be 70 degrees right here. So if I want to be, extra correct, I suppose, this should be, instead of 110 degrees, this should be 70 degrees. If we're going to follow what we have from this picture and the fact that it should be the angle between these two vectors. Luckily, though, if you plug this into your calculator, either the 70 or the 110, because these are supplementary angles, you do get the same result. So they will give out the same answer. So that's a fun thing to check. Better yet, you could try to prove, right, that the sine of theta versus its supplementary angle, the sine of 180 degrees or pi radians minus theta, are equal to one another. So this is kind of an old trig theorem, by the way. So, all right. With that, have a happy Friday, good weekend, all that sort of stuff. Labor Day on Monday, so no class then. I'll see you guys next Wednesday.